Since. So we're going to kind of talk about this changing weather today. Fire. We know it's going to be a good day. That's all it takes. Hey, and just for the record, I did start the fire. That's a song for some of y'all that, you know. Okay. Oh, lights, camera, action. Did you already start? Okay. All right. Hey, okay, so now here's the official welcome to all of you and the rest of the world watching. This is advanced level chemistry here at Spain Park. It is Friday, September the 6th, okay, 2024. So we're excited that you're along for the ride here. This is for all of you that are absent and don't want to miss out on a thing. All righty, so we are starting a new unit. We're going to be talking about the difference between heat and temperature, okay? So what do we know about, well, let me just even say this. Do you remember, and this is really hard, Snowmageddon. I was told that you guys were like preschool, 4K?
Yeah.
4K. It seems like just yesterday, but they were 4K, all right? But in this room, okay, it was about 9:30, and it started to snow. And everybody went crazy that day when it started to snow, because it just doesn't happen that often here. Oh, we need to get out of school, Mr. Hobbs. We need to get out of school. I said, y'all, it's just flurries. You know, it's no big deal. But everybody ran to the window, and they stuck their hands on the window, and it was getting really cold outside, and they put their hands on the window, and what did the window feel? Cold. So why did the hands feel cold? Is it because the cold was coming in from the window? Because the heat was going out of your hands, kind of maybe doing both things? Why did it feel cold?
The window was taking heat from your hands.
Okay. Was cold coming in?
Yeah.
Let me ask you this. How does a refrigerator keep your milk cold?
By keeping it cold.
Traps the cold?
Well, it blows cold stuff, but it also locks the cold air.
Yeah, okay. So, but you're saying that it blows the cold air in, right? How is the air conditioner in this room making it, well, suppose theoretically, making it cool?
It blows it in.
It blows the air in.
Blows hot air, cold air?
Cold air.
Cold air in.
Sits down.
Okay? So the question is what is cold air? What is cold? Okay, we hear the term heat a lot, but what's cold? Okay, the goosebumps, okay? Because it's supposed to get cool or cold, where we're looking for that, okay? Say that again. The absence of heat, okay? That is a very good definition, but what does that mean?
Slow moving molecules.
Slow moving molecules. What does that mean?
I don't know. I think that sounds like.
Okay, say that again. They're tighter together. Okay, they're getting closer because when things cool off, they get more condensed. Okay, let's go this way. If I wanted to make this room perfectly dark, is there a dark switch I can turn on?
No.
There's a light switch, right? So how do I make the room totally dark? Okay. I have to block the light, right? So what would we say is dark?
Absence of light.
The absence of light, right? So in order to make this room totally dark, I have to just remove the light. So I ask you again, how does your refrigerator keep your milk cold?
By removing the heat.
It removes the heat. How does that air conditioner that thank God just turned on?
Removes the heat.
It removes.
So let's talk about that.
It cools down the
Talk
air.
to him, Mr.
Talk to me, Mr. Hobbs. So what is that? So what is temperature? Let's talk then. Let's get your notes out. And you have the notes. And this is the end of that unit. And gonna go to where we stopped.
What are you burning this for?
I am not burning anything.
Why are you heating up the water?
Well, we're gonna talk about that.
Lucas, lock in.
I did. I don't care.
So we've talked about temperature. Who remembers what is the SI unit, the metric unit of temperature?
Kelvin.
Kelvin. Okay? So what does Kelvin or degrees Celsius or even Fahrenheit, what does it measure?
The
The degree of hotness or coldness.
Well, let's even go here.
1 Kelvin equals 1 minus 274.
Okay, so that's the conversion, but what does it measure? It's a measure of the average kinetic energy. Now, you guys learned somewhere in 8th grade, what is kinetic energy and energy of?
Moving.
Energy of motion, okay? So you might want to say this right here in your notes. Energy of motion. Okay? It's the energy of motion. Okay? As the temperature increases, the molecules move faster, right? And out to the side, you probably want to put, we're going to say this all year long. Heat them up, speed them up. Heat them up, speed them up. Heat them up, speed them up. So cool them down, slow them down. So what is the significance of the Kelvin temperature scale? Say that again. Doesn't go below zero. Why not?
Because there's no negative movement.
Say that again.
There's no negative movement.
So what happens at 0 Kelvin?
They stop
It
moving.
stops.
They stop. That's why there's a basement. That's why, how low can you go? Absolute zero. Okay? Absolute zero is as low as you can go. Because heat them up, speed them up, cool them down, slow them down. So as I'm slowing them down, okay, eventually they stop. Now, it's a measure of the hotness or coldness. So if I take an ice cube and put it in my hand, which is hotter, my hand or the ice cube? My hand. So which way does the heat flow?
To the ice cream.
Into the ice cube, from my hand into the ice cube. It determines the direction of heat flow. Heat always flows from hot to cold. But what determines hot and cold?
The molecules.
Because if I take my hand and I put my hand on a hot skillet, which one's hot, which one's cold?
The hot skillet.
The skillet is hot, my hand is cold, right? So my hand is hot compared to the ice cube, but my hand is cold compared to the skillet. So what determines?
The hotter one.
No, but what determines the hotness or the coldness?
Temperature.
The temperature. It always flows from hot, higher temperature, to cold, lower temperature. Right? Now, just we always got to remember then, just the second line is cold is nothing more than the absence of heat. Got hot too fast. Okay? So temperature just measures the kinetic energy, the motion of the molecules. Heat them up, speed them up. Now there is no limit to how fast they can go. When you talk about the temperatures on the sun being millions of degrees, those molecules, I mean, they're just, it's crazy. Faster than Talladega. Okay, and so it's just moving super fast. Okay? but there is a limit. Absolute zero is as cold as you can go. Okay? Now, what is heat then?
A measure of the total potential energy.
All right, so if kinetic energy, you guys have heard of kinetic energy, energy of motion, what's potential energy then?
Energy that's stored.
Okay? It's stored energy, right? It's stored energy. And so we're gonna have to compare. Now, we just kind of talked about this. I'll just go through here. We have our 3 temperature scales. Let me just talk about this real quick before I move on. I jumped ahead of myself. I have 3 temperature scales. I have Kelvin, degrees Celsius, and degrees Fahrenheit.
Can you write this?
I put it on the, you notice I only typed it on one side of the paper, I only print, so I would use the other side to do this, okay? How does a thermometer work? If I take this thermometer right here, how does this thermometer work?
Measuring the speed of light.
Okay, but, when I put it in the hot water, what happens?
It gets hotter.
It goes up, why?
Oh, because
Because heat rises.
It's not heat rises. What did we learn in last unit? What happens with? It lowers its density because what increases? The volume increases. Things expand when they're heated. So the volume increases, so as it heats up, heat them up, speed them up, they move faster, they expand, and it goes up, and we measure as however much it expands, it's proportional to the temperature. Okay? So we have this. Now, Daniel Fahrenheit, a German, way back, he came up with the first temperature scale, because he was seeing, okay, the liquids expand, I can come up with this scale. So whenever you have a scale, you gotta have a reference point. So he had to have a 0 and a 100 reference point. His 0 was a saltwater solution. He lived in Germany, and he found out, okay, if I make a saturated solution of salt water, where does it freeze? And so apparently he went out every winter night, and is there somebody at the door?
The D1 bowling.
Yeah, just get here when you can, man. Get here when you All right, so he went out in German winter, and that saturated salt water. Now you guys know you put salt in around your ice cream maker to make it colder. So salt water freezes colder than just pure water. He found that it froze at 0 degrees. So he marked that at 0 degrees. Okay? That was saturated salt water. Then he used body temperature for his 100 degrees. Now, I don't know if it's because he's going out in a German winter that maybe had a little bit higher body temperature than what we have, because what's normal body temperature in Fahrenheit? 98.6, but are any of y'all kind of like me that it's really not 98.6? Because mine's in the 97s somewhere. Yours is higher than 98, normal, just, so it's hard to tell if you have a fever because you're a little bit there.
Mine's like
99? Yeah, yours is the same, up a little bit? Okay, my normal's like a 97.8, somewhere in the upper 97s is when it's normal. So if I have a 99, I really have a pretty good fever. But he said 100. Okay, and then he divided this up into equal increments. Now on that scale, pure water, what temperature does pure water freeze? 32 degrees. And what temperature does water boil? And on the Fahrenheit scale?
212.
Very good, you read well, Jonathan, 212, okay? Now, those are nice to know, 212, okay? So how many divisions are there? Oh, no, did the wrong one, I was going to 100. How many divisions are there between 32 and 212? 212 minus 32 equals, thank you. Jackson's my mental math man, okay? 180, okay? So there's 180 divisions between the freezing point and boiling point. Well, on the Celsius scale, what does temperature's water freeze at? 0. And what does it boil at? So this is going to be 100. The thermometer is going up the same amount, but now how many units are there between it? 100. You got mental math here, y'all. 0 to 100. Get your calculators out if need be. Okay? 100 divisions versus 180. So which division is actually smaller?
Celsius.
Fahrenheit. There's 180, the same distance. The thermometer is going to go up the same amount. It's just that it's going to be marked differently. The liquid doesn't change on your thermometer. It goes up the same amount. It's just your divisions on it are different. But we have 180 versus 100. Now, we already said, Lucas, what's the difference between Kelvin on the Kelvin scale? What is this 0 Celsius is going to be what on Kelvin?
274.
Not 4, 273. Okay? So this is 0. So this is going to be what?
Negative.
No, not if there's 273 is 0. 0 is going to be.
Negative 273.
Boy, this is an advanced class. Here we go. Negative 273. Now it turns out that this is negative 459.54 or something like that degrees Fahrenheit. Okay?
Is it the coldest that we can do?
That's as cold as you can get. That's absolute 0. What happens to the molecules at absolute 0?
Stop.
They stop. Now, so what temperature is it going to boil on the Kelvin?
Wow.
If it's,
373.
there you go again. 373. Okay, notice it's 0 to 100. Okay, it's just plus 273. So how many divisions are there? 100. There's going to be 100. Okay? But there's 180 between the same on the Fahrenheit. So have you ever done the conversion between Fahrenheit to Celsius? Okay, yeah, because it's crazy. But you remember the 9/5 times the temperature plus whatever? Okay, so do you guys kind of remember that 9/5 or 5/9 ratio in there in the conversion? You don't have to, we're not going to do it, you're not going to be required to do it, but the 9/5, where do you think 9/5 comes from? Well, what's 180 divided by 100 reduced? 9/5. And the 9/5 conversion is because there's 180 divisions here versus 100 divisions here. Okay? Now, there is an unknown system, okay, that is the equivalent to Kelvin. It's called the Rankine scale, R-A-N-K-I-N-E. And the only difference is absolute 0 on the Rankine is absolute 0, so everything's going to be plus 459.54. But nobody ever, ever, ever uses that one. But if you ever want a trivia, it's a good trivia question. Okay? So we have these 3 scales. We just need to know this right here. This is the English version of the absolute scale. Of 0.67, I said 5.4. I trust 0.67 because I probably looked that one up and I probably did this one from memory. Okay? But it's going to be irrelevant because you're never going to have to do that one. Okay? It's just, this is a trivia fact for you. Okay? Remember I call them oh my information? Okay? Oh my information. Okay.
It's like qubits.
So that's just defining the Kelvin scale and the melting points. You do need to know this. You do need to know that as well. Okay. Now let's talk about heat. If kinetic energy is energy of motion, what is potential energy? Stored energy. Energy of position. So I'm going to ask this next question. Is there ever a time that I can add heat? Okay, let's see if I can get this set up now. Okay? I don't know if we'll be able to see this or not. Can you read this from the front and what that says? 75 degrees, right? 76 is going up. Okay, so now as I heat this up, the temperature is going to do what? It's going to increase. So what's that mean about the molecules? They're moving faster. Is there ever a point where I can add heat like this and the temperature not go up?
Yes, when it reaches the same molecule as the flame.
As this reaches the same level, what?
No, when it reaches the same speed as the flame, like when it.
Oh, if it got to the same temperature as the flame, same speed as the flame, is that when it's gonna stop?
Wait,
Yeah.
stop
No,
going up.
no.
Stop going up. Is there a time I can add heat, but the temperature never change?
Yes. Wait, no, because
I-
heat is.
No,
heat is-
no.
How many think yes? How many think no?
Lucas, raise your
How many don't think? How many have never stopped to think about it before and really just don't really care to think about it right now? Okay, well, let's just see what happens in here. But so the first thing I want to do is follow me on this one. Okay? Potential energy. Okay? You've heard about gravitational potential energy. If I raise this up, I just did work. My massive biceps, I crunched it out, okay? And I lifted it up. What did I just do to its gravitational potential energy? Increased it, right? Did this book get hot at all?
No.
But it absorbed, now has more potential energy, stored energy, right? Now I could do the classic thing and drop it, make the big noise and all that, whatever, I'm not going to. Okay? But I had to do work. I put energy into the book to raise it up. Okay? I'm putting energy in. But the temperature is not going up. Because how is the book absorbing the energy?
It's holding it.
Okay, as what type? It's potential energy, right? What does temperature measure? What did we just define it as? The molecules, the book molecules aren't moving any faster. You don't want to stay for the rest? I'm just getting good. Okay? So the molecules aren't moving any faster, but they've gained potential energy, energy of position. So we're going to call this potential energy is energy of position. Energy of position. You change the molecules or the position of one thing to another, it's potential energy. Okay? So now, what's the temperature reading right now?
90-something.
96.9. It's about to go for a while.
Okay? I know, that's why I got people in the front row calling it out, and you're just going to have to trust them that they're reading it correctly.
96.1.
Yeah, 98.6.
1,000 degrees. Okay? Okay, so it's still going up. So we're adding heat and it's still going up. But let's just talk about it. Heat is measured in joules or calories. Joules is really the SI unit. Okay? Where have you heard of a calorie?
It's a unit.
In food. Does anybody know the definition?
It's like something.
The amount of heat needed to raise 1 gram of water.
What?
Is that on there?
Yeah.
Where?
I don't know.
It's on ours. It's on ours.
Our paper's different.
It is?
Yeah, ours, I already have it. I already have it.
Your answers are all in there already?
Yeah.
Oh man, I ran off the wrong one. All right, calorie. Okay, so it's the amount of heat needed to raise 1 gram of water 1 degree. So this is going to be 4.184 joules. Okay? Now here's the deal.
He's got 4.18.
That's fine. I just go a little bit more sig figs.
Oh,
I need to have you fill in something. You know, got to do a little work for yourself. Okay? So I just give you another sig fig, 4.184. Okay, what's the temperature now?
It's boiling.
100.5.
100.5.6?
100.6.
Okay? All right, so let's just keep watching now. So it went from 96 up to 100.6.
Wait, what reason is the boiling?
Okay, so now let's just kind of see what happens here. But while we're doing that, while we're waiting to see, let's talk about this.
Heat's leaving because it's.
When you look at a Snickers bar, and it says that it's 280 calories in that king size Snicker bar. Okay? That's really a food calorie. It's supposed to be a capital C. They never put capital C's, but it's supposed to be a capital C. All right? A food calorie is actually a kilocalorie, which is 1,000 calories.
What?
So it's actually.
So it's really 280,000 calories. which gives more meaning to a moment on the lips, forever on the hips. Okay? You know, thank you. I'm not all that. So, now the good news is that a nutritional calorie, when you go and you burn a calorie, you're also burning nutritional calories. However, it's still not right because you got to go run like 25 miles to burn off 280 calories. It takes you like 3 minutes to eat a Snickers bar, and then like 10 hours to burn off the calories. Just, I'm really going to have a conversation with God about that one when I get to heaven. Okay? Just why does it have to be so difficult? Okay? But this is your food calorie. Now, what's the temperature?
It's turning off.
It's turning off.
Whoa.
I'm telling you, it's gonna
Blackout.
get getting hotter.
It's plugged in.
If it's left on, you just turn it on.
Well, but I mean, there we go.
101.
It's not. I love our thermometers. Okay, we're just gonna keep watching it. All right. Now, heat is a measure of your potential energy. Okay. Heat is a measure of the molecules' positions to one another. So right now, I'm gonna spill water all over your table. Okay, so here are water molecules. They're being stuck together, and we're gonna learn later on in the year what holds them together and all of that. Did you learn about hydrogen bonds at all in biology? So you have hydrogen bonds holding these all together, but if I want, another deep question.
Deep thinking.
What's in the bubble?
Air.
Okay, where's the air coming from way down there?
From the
But the bubble's forming at the bottom.
The water is separated.
Okay, okay, you guys are right, but they're all still thinking it's air.
H2O.
Okay, is it hydrogen and oxygen?
No, it's oxygen.
What's the white stuff coming off?
Oxygen.
What is steam made up of?
Evaporated water.
Water. So what's in the bubble?
Water.
Water vapor.
Water vapor. Okay? Okay, we all think it's air bubbles. Not we all, y'all. Okay? Except for these two. Okay? Most people just think it's air bubbles. Hey, Lucas. Lock in. Okay? But it's not. And it's not hydrogen and oxygen because it's still steam, it's still water vapor coming off the top. So all that's happening is the water molecules are breaking apart from one another, forming steam, which is water molecules separated in gaseous form. So you're having to break a bond. Now, does breaking a bond give off energy or require energy? It requires energy because you guys know breaking up is always hard to do, right? If you're gonna break up, you gotta put energy in. Now you guys are lucky because now you guys can just break up on text. You know, hey, can't we just be friends? You know, but back in my day, she would always have to call me on the phone or we do it in person. Yeah, it's always like, hey, I think we should just be friends. Are you sure? Are you sure? Yeah, I'm pretty sure. Yeah. So you need to understand that breaking up is hard to do. But look, so when we do this, we break them and change the position, but we don't necessarily make the molecule move any faster. We change its potential energy by breaking the bonds. Now that energy is stored because we put energy in. Just like I lifted the book up and I put the energy into it, it stored it. It didn't get hot. It didn't change in any way. It just stored the energy. When I put the energy in to break these apart, they now have the potential to come back together again. Okay, so, baby, come back. Any kind of fool can see I was wrong, I just can't live without you. Let's get back together. Okay, that's a song, by the way, thank you very much. Somebody knows some good 80s music. Okay? Hey, so when the bond comes back together, now look, when bonds form, that's when the sparks fly. That's when things heat up. Okay, and so, so the same amount of energy, now listen, the same amount of energy that it takes to break the bonds apart, if you reverse the process and make the steam condense, come back together and make liquid water, like it does like on iced tea glass, you know, the water condenses. The same amount of energy you put in to break it apart is released when it comes back together. But molecules don't go faster or slower. You're changing their relationship. Whenever you break bonds or form bonds, you're changing potential energy. You are not changing its kinetic energy. So what's the temperature now?
101.
Oh, it's still 101?
Yeah, it's like
It's
101.0.
But it's been 101.0 for like 5 minutes and I'm still adding heat.
Oh,
It's expending its energy to break up the steam.
Okay, say that again real loud for those people in the back to hear, because you're 100% right.
It's expending its energy to break off into steam molecules.
Okay? He's using the word expending. I'm just going to change his definition from expending its energy to absorbing or using the energy that's being added to it. Instead of making the molecules move faster, it's making them break apart. Okay? It's breaking the bonds. When you break bonds, it's a change in potential energy that the thermometer doesn't measure. We call this latent heat. Is that on there somewhere? Phase changes involve changes in potential energy. Okay? Is the word on there anymore? Do I need to add it in? Okay? So this is huge. This is hard. This is something you've never heard before. Okay? So we need to really just be thinking, you know, about this. This, when you have a phase change, what are our phase changes? This is what to what?
Liquid to gas.
Liquid to gas. So boiling. What are some other phase changes?
Solid to liquid.
Solid to liquid. So if I want to make an ice cube melt, I have to put energy in and break the bonds and let them go from being locked in place to being able to move around. Okay? That requires, anytime you break a bond, you put energy in. Is that endo or exothermic? Putting energy in. Endothermic, it's entering. Okay? So putting energy in, it's a change in potential energy, which the thermometer doesn't measure, so we call it, it's latent heat. This is a good vocab word. It's latent heat. Latent means hidden, and it's hidden to the thermometer. Hidden to the thermometer. What's the temperature? What's it say right here?
Turning off again.
Okay?
101.
Still 101. Okay? It's going to stay. Now it's supposed to be 100. The temperature probe needs to be calibrated just a little bit. When you have a good, you know, this is 23 years old. When you have good equipment,
Also, needs the other glasses.
well, but it's in the glass. The glass is all that should also be the same temperature there. Okay? So, we call this latent heat. If you take physics, instead of, we're going to use this, the heat of fusion, which is going to be delta H sub F. Okay? What does the delta mean? Change in. If you don't know that, maybe put that right there. This is a delta, it's a Greek letter, which equals change in. Thought you weren't going to have to write any notes. You thought I had all the answers in there. Okay? The change in, it's the heat of fusion. But if you take physics, they don't use delta H sub F, they use L sub F for the latent heat of fusion. It's latent means hidden. It's hidden to the thermometer. These changes in potential energy are hidden to the thermometer. The thermometer doesn't measure them. You have to measure them in what's called a bomb calorimeter, or in a calorimeter. In a calorimeter. So if I take this quiz that you just took, okay?
Oh,
Is that paper hot? Okay, I'm gonna get a female perspective. Is this paper hot?
Dang.
No, okay, it's just normal paper, right? It's not hot. Okay, but I go and I'm gonna put just a little bit of energy into it. Okay, now, will you grab this now?
I don't think I wanna.
Yeah, I will, okay, I will. I'm glad Mr. Britnell left because maybe the fire marshal, okay? So where is all of this heat coming from? Okay?
The burn, the
Fire,
combustion.
bump, 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 bump. So a whole heck of a lot more heat, okay, is being given off, okay? Where did all that heat come from?
Potential energy.
It was stored energy, so when you burn the paper, it's cellulose, it's a whole bunch of carbon, hydrogens, and oxygens all stuck together.
So it undoes the bond.
Did it turn off? I just fell
No,
over.
no, it just like.
Okay, you got it. Okay, so listen. So you got carbon, hydrogen, and oxygen all stuck together in big molecules. Listen, listen, listen. That's just paper burning. You smell that all the time. Okay? But when it burns, the atoms rearrange, and we make a whole bunch of carbon dioxide, a whole bunch of water vapor, and then there's the ash. So the atoms have all completely rearranged. Okay? Now, I don't know how much energy, potential and kinetic energy or total, are in that piece of paper. I don't know how much potential energy there is total because the electrons are all moving, the bonds are breaking, the molecules are all bumping off of one another. There are way too many variables to be able to measure it. But I can measure the amount of heat that was given off. I can measure the change in the temperature. So what do you think a calorimeter measures?
Change in.
Okay? A calorimeter probably measures calories. Like a calorie meter. I mean, real deep, naming system here. A calorimeter. So you have in this calorimeter here, a little less glare, okay? This is, they call it a bomb simply because you're gonna burn it. It's not really a bomb.
Oh, it's a bomb
Okay.
because it has potential energy.
No, it's a bomb because you're gonna burn it, okay? So you put your sample, so if I wanna know, how do they know that Snickers has 280 calories? They dehydrate, they get all the water out of the Snickers bar, they put a sample of it into the bomb down here.
Wait, for real?
For real. For real. Okay? They put it down in here, and they have electrical wires, and then they put electricity, and then they burn the Snickers bar. Well, when it burns, it gets hot, right? It gives off heat. Well, that heat is going to get transferred to all this water that's around it. Well, we know that a calorie is the amount of energy it takes to raise 1 gram of water 1 degree. If I know how many grams of water I have and how many degrees it goes up with my thermometer, I can measure how many calories must have been, how much calories were absorbed by the water. And the law of conservation of energy says energy is neither created nor destroyed. And so whatever energy was absorbed by the water had to have come from the Snickers bar. So the heat lost by the Snickers bar was gained by the water. And just for the record, on Monday, we're going to get to look at doing the math on those type of things. Okay, just, I know you guys love being able to do these math things. Okay, so we're going to heat this up. We burn it. The heat is released to this, so the calorimeter can measure not how much energy was in the Snickers bar to start with or how much is at the end, but how much is released when it burns. Now, it is assumed that that same amount of energy is released when it burns in your gut. So you eat the Snickers bar,
Potential energy in the Snickers
you
bar.
breathe in the oxygen, your blood carries the glucose, the sugar, to your cell. The hemoglobins carry the oxygen from your lungs to the cell. Do a little biology here, okay? And then at the cell, the sugar and the oxygen combined burn. The sugar burns, releases carbon dioxide, which we exhale, and produces water, which we get rid of other ways.
So every time you breathe, you're burning sugar.
Every time you breathe in, that oxygen is going to your cells, and your breakfast is being consumed and turned into energy. Okay? And so, and it's really pretty much the sugars that are being consumed in your cells. Now you have proteins and other things that you eat that go and do different bodily functions that I didn't take anatomy, so I don't know everything that goes on. Okay? But I do know that the energy source is the sugar and the oxygen burning at your cells, changing its potential energy. So then your body uses that. Now, here's some more trivia for
What
you.
about the stickers bar being chemical energy?
Here's some more trivia. How many calories is equal to a pound of fat? What's the ratio? How many calories do you eat to gain a pound?
1,500.
More than that.
2,400.
More than that.
10,000.
Less than that.
5,000.
8,000.
Less than that. Less than that.
35.
Less than that.
3,500.
More than that.
35.
3,500. Bingo. Oh, he's been saying in the back. I'm sorry, I didn't hear it in the back. Okay. Okay. So Jackson obviously heard Hudson say it. Okay. Now listen. 3,500 calories. So if you consume 3,500 more calories than what you burn, then you're going to gain a pound. The reverse is you have to burn 3,500 more calories than you consume to lose a pound. All right? Now it's hard to burn 3,500 calories. That's the problem. Now we have base metabolic rates. Now girls, I am really sorry about this. But your base metabolic rate is somewhere you just sitting, breathing, and staying alive. You burn 1,800 to 2,000 or so calories just there, just to live, just to breathe, just for your heart to beat, your lungs to work, your body functions to take place. Guys' basic metabolic rate, though, is anywhere from 2,400 to 2,800 calories. Okay? So guys just naturally burn more calories. Now, the more muscle you get, the more calories you burn just in your basic metabolic rate. So as you work out, you just tend to get more muscles, yet you can eat more and not gain weight because your basic metabolic rate is greater. Okay? Now, this is my workout, with the remote, sitting on the couch, eating the chips with the dip. Okay, and so as a result, I've consumed more calories than I have burned off, and so I am storing them for future use. Okay, in case a crisis emerges, I'm ready. Okay, so when the apocalypse comes, I have something to live off of. Okay,
You'll survive on the deserted island.
that's right. I'll survive on the deserted island longer than the rest of y'all. Okay, unless you decide to kill me and eat me. All right, yeah, I know. Yeah, so, okay. So when we're measuring heat, we cannot measure heat directly. We can only measure changes in the amount of heat. So a calorimeter measures that. So let's go back to just finishing up this little thought process right here. Okay? So we call the heat needed to cause 1 gram of ice at 0 degrees to become 1 gram of water at 0 degrees, just to break the bonds holding them together. Now you're really just kind of stretching and bending those bonds because they're still right next to one another. We call that the heat of fusion. Okay? For ice, it takes 334 joules, which is 79.9 calories. And that's not a kilocalorie, that's a calorie. To make 1 gram of ice at 0 degrees become 1 gram of water at 0 degrees. So we're going to end the day with this question. What temperature does water freeze? 0 degrees Celsius, right? We just said that. So what temperature does ice melt?
Wait, no, 100 degrees. Anything under.
0.
Anything above.
Okay.
2. Anything
So
under 2.
we think, it's just natural, we think, well, if water freezes at 0, then the ice has to melt at 0.0000001, something above 0 degrees. That's not true. Because what type of energy is involved in phase changes? Right? Just what type of energy is involved in phase changes? No, kinetic energy is what temperature measures. Phase changes involve what? Potential, which is hidden to the thermometer. So this is potential energy. This heat of fusion is potential. So we're adding heat, just like we were adding heat to make it boil. We are adding all of this energy to make water boil. The heat of fusion is equal to, oh, I'm having a senior moment, 2200 and plus 2250 joules, 539 calories you have to put in to make 1 gram of water at 100 become steam. So I was adding all of this heat. I never turned the flame off. The temperature didn't go up because all of the energy was being consumed, used as the heat of vaporization, which is potential energy, which is latent, hidden to the thermometer. So what temperature does water freeze? 0. What temperature does ice melt?
0.
0. Do they have the same kinetic energy? Yes. Do they have the same potential energy? No. The water has absorbed 79.9 or 334 joules of potential energy that when the water comes back and freezes, it can release, which we'll talk about on Monday. Well,